So, greetings, everyone. We continue with our second lecture in 2026 on nanodiamond material. And we have an excellent speaker today, Arsène Chemin from France. Let me give a short bio that Arsène provided. Arsène is an associate professor at the University of Lyon, France, and a researcher at the Institut Lumière Matière. His works centers on the physics and chemistry of surfaces and interfaces, with a focus on diamond materials for quantum technologies, photoelectrochemistry, and sustainable energy solution. Using synchrotron-based X-ray spectroscopy combined with laboratory experiments, Arsène investigates interfacial phenomena to design high-performance materials for real-world applications. His research bridges fundamental science and theory with applied innovation, fostering collaborations between academic and industrial partners to develop next-generation materials. I attended Arsène's lecture a few months ago in Paris at Nanodiamond Symposium, and it was an excellent lecture, very insightful, and I enjoyed it so much, and I'm happy that Arsène joined us for Adamas's lecture series. So, Arsène, we are all ears for your lecture.
Yes. Well, thank you. Thank you very much, Olga, for this very kind introduction. And thank you, of course, for inviting me today. So indeed, I will, during the next hour, try to talk a bit about how surfaces of diamond can be so important for many different applications, in particular quantum and catalytic application. So as Olga said, I am mostly interested in surface and interfaces. So my work is a lot axed on catalysis and photocatalysis, electrocatalysis, but exactly what happens at the interface at the nanoscale. To do that, to make those kind of study, I developed during the last year a bit of a technique, I would say, where I study very different designs of material and different synthesis of material. I don't do much myself, I have to confess. I usually rely on very talented collaborators to provide me with interesting samples. And then I study them first in laboratory, doing quite simple and basic lab characterization to look at the properties of the materials and the photoexcitation. I mean, how they can get photoexcited, basically what wavelengths, etc. But what I also do is I often bring the sample to the synchrotrons. So I did work quite a lot at BC2 synchrotrons in Berlin, where we can do spectroscopy ex situ, but also in situ in order to really investigate what happens at the surface and at the interface. And basically today I want to talk about surface of diamonds and how we can use those measurements in synchrotrons to really understand and bring a new enlightenment of the surfaces. So the way I prepared this talk is in two big parts. So the first part is a bit more introductory and a bit more, I would say, theoretical, where I will talk about diamonds. So I know most of the viewers here probably know diamonds even better than I do, but I like to remind myself how strange diamond can be. So I will just talk briefly about that. And then I will introduce to you to which extent the diamond interface are actually important and how can we understand theoretically the interplay between the surface state and the electrochemical or even just electrical properties of diamond. After maybe a short break, because I know from my students that the attention span of people is not that long, I will talk a bit more about the synchrotron itself. So I have a few pictures to show you because accessing the inside of the synchrotron is not always something easy to do. And then the two last parts are really, like, I would say, deeper, more scientific expose on the stabilization of the charge of NV centers through the surface states of diamond, and also how we can leverage the surface state of diamond to do some photoelectro reduction of CO2. But first, let's talk a bit about diamond. So diamonds are really strange. When you think about it, diamond is only made of one single element, and this element is actually one of the most common on Earth, carbon. And yet they are quite fantastic. As Professor Collins used to say, carbon in its diamond phase have been fascinating scientists for at least 300 years. So it's 300 years that we are trying to understand that stone, and we are still working on it. It's also quite interesting to think that the crystalline phase of diamond is rather simple. It's the most dense one. And yet, by simply changing the graphic phase and going to graphite or graphene, we completely change the properties. It doesn't look the same, but it also behaves very differently. We all know that graphite and graphene are very conductive material. But diamond, on the other hand, is a semiconductor with a particularly wide bandgap. And this will become quite handy in the following of the talk. It has a bandgap of 5.5 eV, which is very hard to excite, which can be a problem for photocatalytic application. But it can also host a lot of defects that we will see, and that is quite interesting. One thing that I'm always amazed about is just to remember that diamond should not be. Diamond is actually a metastable phase of carbon material. At room temperature and room pressure, we should only have graphite or graphene. And that makes diamond particularly hard to synthesize. And yet, in the last, I would say, 10, 20 years, so many progress have been done in that field that we can actually now consider diamond for many different applications. And I think we really have a chance here to democratize diamond as a wonderful material. It is metastable, and at the same time, it is incredibly resistant. So diamond, probably the main use of diamond today in the industry is for grinding. So it's actually the hardest stone we know on Earth. And it's also extremely chemically stable. And that is particularly handy if we want to do electrodes with diamond. So lots of my research concerns electrodes made of boron-doped diamond, which is conductive. And as I will explain, they have many interests, but one of them is that they never wear out in comparison to other kind of electrodes. And finally, as I said, diamond can host many defects. So on this picture here I took from the Stuttgart University website, they are all diamonds. So diamonds is not only this transparent boring stone, it can have many different colors because it can host many, many different defects. And just to give you a hint of it, my colleague at the lab has this huge book about optical properties of diamond, which has nothing less than 285 figures and many tables, 21 tables too. So that's just to give you a hint of the extent of what happens in diamond material. And those defects are actually very useful. So I guess many of you here know about NV centers that can be used for quantum probing. I will actually talk more at the end of the talk. But there are also many other defects, and some colleague of mine, Gilles Ledoux at the Institut Lumière Matière, actually worked extensively on nickel nitrogen vacancies that can be used to measure temperature in system. So you can disperse nanodiamond with those kind of vacancies inside a medium, for instance, liquid, and like look at some cavitation effects probing the local temperature. So diamond have many, many uses, and many of these uses are coming from the defects. But what a better defects than an interface? When you think about it, interface is nothing more than a huge amount of defects. Every time you cut a crystal, you necessarily create defects. you have to break bonds, you have to reorganize the surface, you have to create lots of things that can be excited, that can lead to charge separation, charge trapping, interact with the surrounding environment. And those interfaces are the source of so many interesting behaviors in diamonds. But as Wolfgang Pauli said, if God made the bulk, surfaces were invented by the devil. It is extremely difficult to study interfaces because they are so small. Simply, if you consider a diamond, you will have billions of atoms consisting in bulk, but only a bunch of them will actually be at the interface. So understanding and probing the interface is not an easy task. But today, I propose that we play a bit with the devil and we try to understand a bit more the diamond interface and how we can actually study it. So in this section, I would like to make you understand how important the interface of diamond is. So as I said, when you cut the diamond, you have to terminate it. And in many semiconductors, like for instance, silicon, the silicon will tend to end with an oxide layer, like silicon oxide, a few nanometers or tens of nanometers. In the diamond, it's not the case at all. You cannot have an oxidized surface of diamond. I mean, you can have oxidized surface, but it's not an oxide layer. It will actually be oxygen atoms that will bond to the carbon atoms at the surface, just like on that picture. And those terminal atoms will behave similarly to small molecules. And you can also have surface reconstruction, meaning that you can have different carbon atoms that will bind together, forming some sp2 bonds instead of the classic sp3 bonds of the diamond. On top of that, so you have many different facets that can lead to different bonding configuration. But of course, you also have some facets that can be cut in weird ways with some jumps and some stairs kind of cut in the different crystallographic plane, leading to even more possible bonding environment of the surface states. And of course, you can terminate diamond with many different atoms. So I just talked about oxygen, but as you know, when you grow diamond by CVD, so the main termination is actually hydrogen. So you will have clean hydrogen layers at the surface. But that's not even all. You can even have different kinds of atoms, such as nitrogen or fluorine, that have been more and more investigated in the late years to terminate diamonds. And all this is very interesting because by using this kind of termination of diamond, you can actually have a very nicely passivated surface. So one good example of that is the use of boron-doped diamond for electrocatalysis. If you look at this diagram showing the current density of various electrodes depending on the potential that you apply, you can see that the boron-doped diamond in red here is flat on a very large potential window. It's actually one of the largest potential window you can achieve. So between -1 and +2 volt versus, I think it's hydrogen reference here, you don't have any reaction. Because if you look at platinum or gold, you can see those features here and those peaks that actually corresponds to redox reaction. But the diamond surface, because reacting so little with the environment, it remains completely flat. So it makes boron-doped diamond electrodes very good substrate in order to understand and probe the electrocatalytic properties of other materials on top of it. It also has very little capacitive behavior. So if you look at the glassy carbon here, you can see that the cycle here is slightly open. So that basically means there is some capacitive behavior at the surface and at the interface that you barely see on boron-doped diamond. So diamond is actually great for catalysis. Very bad for creating hydrogen, unfortunately, because it's completely passive, but very good for probing other materials. Now, if you look at, if we come back to this table here, you can see that the different colors of the elements corresponds to the electronegativity of the atoms. And depending on the bonding, on the element that you will bond to the surface of the diamond, you will actually change the surface properties. So if you look to the right side of the carbon, you have nitrogen, oxygen, and fluorine, which are more electronegative than the carbon, which means that they will tend to pull out electrons out of the carbon atoms, and that will lead to a positive electron affinity of the surface. So what does that mean? Well, it means that if you consider the bandgap of a diamond, so these diagrams here are extracted from this very nice article from 2023, where they compared the band position of many different nanodiamonds. You will see that for oxygen nanodiamond, the bandgap would be much lower compared to the vacuum level. And the conduction band will be lower than the vacuum level. And this is what we mean by positive electron affinity. So the way you can understand that is that if you have the surface of the diamond, which is covered with oxygen, that pulled out electrons from the crystal and that are overall slightly negatively charged, if you excite electrons to the conduction band of the diamond, they will struggle to exit the surface. There will be some kind of energetical barrier to overcome. And this is the positive electron affinity. On the other end, you have the hydrogen on the left side of carbon. And because it's on the left side, it's less electronegative, meaning that it will lead to a negative electron affinity. And if you check on the measurement, you find out that indeed the hydrogen terminated nanodiamonds have a conduction band lying above the vacuum level. And that is very interesting, because what does it mean? It means that every time you excite electrons to the conduction band of the diamond, those electrons will tend to simply escape from the diamond. And this property is quite unique. I don't have in mind any other material that has a conduction band lying above the vacuum level. So diamond can emit electron in vacuum. That is already known since a long time. But as we will see, they can also emit electrons in liquid environment. And that is very handy, because those electrons that are then in the liquid environment are very reductive and can be used for electrocatalysis. Another thing which is particularly interesting in diamond is the zeta potential. So the zeta potential is a potential that we can characterize on colloidal solution of nanoparticles, generally speaking. And the idea is the following. Every time you disperse some nanoparticles in the liquid, the nanoparticles will get charged, either positively or negatively. And this surface charge will attract ions from your liquid that will create the Stern layer and like various double layer, Helmholtz layer, etc. And those ions will be carried out with the particle. And what we call the zeta potential is the electrical potential happening at the slipping plane here in the electrolyte. And this electrical potential will vary depending on the ions that are around the nanoparticle. So simply put, the zeta potential is a way to measure the surface charge of the nanodiamond. And this charge has a huge impact on the colloidal stability of the nanodiamond, for instance, if they aggregate or not. And what was measured already in 2010 by Williams and al. Is a very strong difference between hydrogen terminated nanodiamonds that have a positive zeta potential and oxygen terminated nanodiamonds that have a negative zeta potential. And that can be quite surprising, but as we will see, it's actually very understandable from what I just explained before. And this difference between hydrogen and oxygen termination has been observed many times by many groups, and I want to talk very briefly about the work of Arnaud and Petit, who did also very interesting measurements and developed a very nice understanding of the zeta potential. The surface states also have a huge impact on the photoexcitation of the diamond because, as I said, they will behave like molecular states. So you can think about the surface state of diamond as small molecules having occupied and unoccupied orbitals at the interface. And thanks to X-ray spectroscopy, actually, we were able to completely map the position of the surface states with CH, sp2, CO, CH, etc., within the bandgap. And that is particularly interesting because those surface states can actually be photoexcited within the visible light. So even though the diamond bandgap is very wide, 5.5 eV, those photoexcitation happens, and we can use that to do some chemistry and, for instance, use diamond electrodes to reduce CO2. One very nice paper that showed that is the paper from Büchner and al. From 2022, where they looked at the emission of solvated electrons from nanodiamonds. And they were able to show that solvated electrons were produced from the excitation and the photoexcitation of H-terminated nanodiamond, but not really, at least not in the visible range, by the photoexcitation of oxygen-terminated nanodiamond. And the way they explained that at that time was the existence of some surface states of the sp2 carbon that enable the visible excitation of solvated electrons from the hydrogen nanodiamond. So since then, various works exist also on the production of solvated electrons from diamond surfaces. I've been working quite extensively on that. And to be completely honest, I think there's still a lot to understand because the photogeneration of solvated electrons depends a lot from one sample to another. And I don't think the community still have a very great understanding of it. So if you're looking to produce solvated electrons, please feel free to help us understand it better. So I talked about a lot about electrochemistry, but I think many of you might actually be interested in quantum sensing and NV centers. As it has been said in that paper from 2014, certain types of coverage on diamond surfaces may lead to blinking and blinching due to the presence of acceptor surface states. And indeed, we understood since then that depending on the surface termination, hydrogen, oxygen, or nitrogen, as I will explain later, we can have many different charge trapping happening and blinking of the surface states. And of course, I cannot even be exhaustive here. I talked about what I used to work with, but there's even more. Diamond and surface of diamonds are very important for electronics, also biology with the interaction with cells, for instance, but also in various different kind of probing. I will talk about NV centers, but there are all the other color centers that can be used, etc. So here I only scratched the top of the iceberg, but I hope you understand how much surfaces can impact the use of diamonds. So now that I tell you that, you must say, well, that's very interesting, but how can we process that? So how can we understand all these surface properties? And in order to understand the surface properties and the effect of the surface, let's do chemistry like physicists. I'm a physicist. I am trained as a physicist, and yet I'm doing a lot of chemistry lately. And I like to see the interface as a junction, the same way we can have a junction between, in that paper, for instance, diamond and I forgot the name, transition metal oxide, sorry. We can actually see the interface of diamond and liquid the same way. So in the physics of semiconductors, every time you put together two semiconductors, you will have a mismatch of the Fermi level between one and the other conductor, and that will lead to a charge exchange. So you will have electrons going from the semiconductor having the highest Fermi level to the semiconductor having the lowest Fermi level. And this will lead to a charge depletion layer and band bending. So basically you will have positive charge on one side, negative charge on the other side. That will create an electrical field that will compensate the initial mismatch in energy between the electrons. And we can do exactly the same reasoning with diamond and the environment. So on one side, you will have the physics of the diamond with the valence band, the conduction band, positioned according to the vacuum level, depending on the surface electron affinity, as I was talking. And on the other side, you will have the electrolyte, so the chemistry part. And in the electrolyte, what will play the role of the Fermi level is actually the chemical potential. So in case of water, this chemical potential is around 0 or 1 versus hydrogen. When you put those two words together, you can see there is a mismatch between the Fermi level of the diamond and the chemical potential of the environment. And this mismatch will lead to some electrons of the diamond, in that case, to jump into the surrounding of the electrolyte. I can only recommend this book if you're interested in semiconductor electrodes, which is a very good book. And this charge depletion layer here will create surface band bending of the diamond. By the way, that also works for adsorbate. So if you're working in air, for instance, and you're probing some sample with a diamond probe, you will have the same kind of charge transfer between adsorbed molecule and the diamond. And this framework is actually very useful because we can really understand a lot from it. So on the diamond side, the Fermi level, for instance, will be completely dominated by the different doping and defects. So depending if you're working with boron doped diamond, nitrogen doped diamond, or just pure diamond with defects, you can see like some variation of the Fermi level. On the other side, well, it's basically chemistry. So you have the electrolyte, often water, which is well defined, or some adsorbate with CO2, water molecule, etc. You will have at the surface of the diamond, the surface termination, so hydrogen, oxygen, nitrogen, fluorine, that will change the electron affinity, and so the position of the valence band and conduction band. And finally, you will have the equilibrium at the interface. And this is actually was not so well understood lately. So this kind of approach where I really look at what's happening at the interface, I actually demonstrated this kind of reasoning recently on electrodes for hydrogen reduction. So if you're interested a bit more on the theory, I have a paper which is open source, but I can also send it to you. And all this framework is very handy. So let's see how we can use it. So what we can do with this framework is, for instance, understand the surface delta doping. So many of you understood that H-terminated diamond is actually conductive at the surface, even if it's not doped. To be frank, when I started working with diamond and people tried to explain me that, I had a very hard time to understand what was happening there. And what was happening is actually rather simple. When you have the equilibration between the Fermi level of the diamond and some adsorbed molecules like water, you will have a band bending which is so strong that it will cross the Fermi level of the system. And this will lead to holes in the valence band at the surface of the diamond, and this basically behaves like a metal. So this is how we can very easily understand delta doping. What we can also understand is the zeta potential. So I told you about the work on Petit and al. They made a very nice description of the zeta potential using a very similar theoretical framework, where you have the equilibration between the Fermi level on the nanodiamond and the environment. The only little thing I could say is that in nanodiamonds, you actually cannot really consider bond bending because the nanodiamonds are so small compared to the charge depletion layer, then they just charge overall. So you would have positive or negatively charged nanodiamond. We can also understand the surface oxidation of the diamond. So as you probably know, if you have a hydrogenated diamond and you let it in the air, it will tend to oxidize with time. And so I will talk a bit more about that, but we can also understand that. And generally speaking, we can really understand what happens at the interface of diamond electrodes. So for instance, I can give you an example with the boron-doped diamond. So boron-doped diamond is a material which is great for electrochemistry. I studied quite extensively this kind of diamond black that was developed by Peter Kniton, which is a nanostructured, heavily doped boron-doped diamond. And to study it, we can perform some very simple electrochemical measurements. So that's a measurement I developed in Berlin during my postdoc, where we have a light that we shine through monochromator, and then we shine the diamond electrode inside an electrochemical cell. And because the light is chopped, what we can do is that we can run classical CV curve, but with the chopped light on top of it. And that will give you the electrochemical behavior of the diamond here. But if you zoom in, you can see fluctuation in the current corresponding to the dark current, and on top of it, the photocurrent, which is triggered by the light. And we can use this light in order to probe the diamond interface and bond bending. So for instance, if we excite the diamond above the bandgap and there is an upward band bending, the electrons will go in the inside of the diamond electrode, and that will give a negative photocurrent, as you can see here. But if we start to apply a potential, we raise the Fermi level in the diamond electrode, and that will change the direction of the bond bending. And then when we photoexcite the diamond, this time the electrons will go in the liquid, leading to a positive photocurrent here. And we can do that for many different potential, and we can have this kind of curve here that you might recognize as being Schottky diode. So as I said, you can consider the diamond plus the electrode as semiconductor, and in that case, it would be a metal. And indeed, the diamond interface behaves exactly like a Schottky diode. Very bad one, actually a very terrible one, because if you look at the ideality factor in the behavior, it's actually huge. So it has a lot of defects, of course, but the description and the mechanics behind it is exactly the same. When the photocurrent is zero here, it's what we call the flat band potential. It's basically the potential at which the band is completely flat. Leading to no particular preferential direction for the photocurrent. And what was quite amazing in this study we made is that we changed the surface state of the diamond. So the first curve I showed you was for fluorinated diamond surface. And here we have the curve for the oxidized diamond surface. And you can see that the behavior is the same, but the flat band potential is not. And from what I told you, it's actually very easy to understand, because if you change the surface state from fluorine to oxygen, you will change the negative electron affinity at the surface of the diamond, meaning that the position of the band versus the vacuum level will shift. And this will also shift compared to the chemical potential of the liquid. So basically, the potential you have to apply in order to obtain flat band will not be the same depending on the surface termination. And one thing we saw is actually if you monitor the flat band potential along the CV curve, we can find very interesting behavior. So to do that, we performed the CV curve with the light on top of it, and we extracted the photocurrent along the CV curve. And when we start here at the beginning of the cycle with an oxidized diamond surface, we just move the potential, and we find at this point here at around plus 0.6 volt, the flat band potential of the oxygen terminated surface. So in that case, the photocurrent was 0 for this potential. And then if we continue cycling, we can actually observe here on the CV some reaction happening. And this is actually the reduction, so the electrochemical reduction of the diamond surface. So this happens because at some point, the potential of the electrode is above the reduction potential of the hydrogen. So we start reducing water, forming hydrogen ions and radicals that will reduce the surface of the diamond. And if we keep going, we will at some point measure a novel flat bond potential, which is much reduced compared to the previous one. So you have this beautiful hysteresis inside the photocurrent. And this flat bond potential corresponds to the hydrogenated terminated diamond. So it's another proof that we really managed to change the surface state operando, I would say, through the electrocatalysis of the surface. And this can actually go again and again and again, because at the same time, when we go back to positive potential, we will again oxidize the diamond surface. And this we were able to demonstrate happens when the Fermi level in the diamond goes below the occupied surface stage at the surface of the diamond. So you can imagine that we forced first the hydrogen to stick to the diamond surface. This will create some bonding environment. But if the potential drops too low, it will pull out electrons from the CH surface states. And those CH surface group, now positively charged, will be very reactive and will tend to oxidize. And if you put the numbers together, you actually find out that it is almost, if not always, systematically the case every time you put diamond in water. So this is actually why hydrogen terminated surfaces are not stable in a liquid environment or in air. It's because the chemical potential of the liquid environment is enough to drive the oxidation of the surface. One other thing that we were able to demonstrate also is that light can also trigger some photoreaction and some electrochemical reaction at the surface. So we can also photo-oxidize and photo-reduce the diamond surface. So that's it for my quite long introduction already, because I've already been talking quite a lot and I know you probably all feel already tired. I might make a very small break and maybe take one question.
Okay, who can step forward and ask a question during a break? Abe, do you have a question? You always have questions.
Maybe I can ask one.
Please.
So I'm John Owen. I'm a chemist. You described electrons transferring into the solution to generate hydrogen radicals, which then reduce the surface. And I wondered whether that makes sense or whether transfer of charge to the surface then causes a reaction with hydrogens or, desorption of ions. Do you need to invoke electron transfer into the liquid?
So when I invoke electron transfer, it's actually to set the equilibrium of charge. So I don't mean by that there is an electrons going to the electrolyte. What I mean is that there is the charges that will equilibrate. And this I actually demonstrate in the paper that was just accepted a bit above. I can send you the link. That actually happens anytime. Every time you put a metal or an oxide inside a liquid, this is actually the origin itself of the Helmholtz-Doppler layer, this equilibration of charges. And it's not.
But I'm
really
referring to the functionalization that you described, yes. Right?
Yeah. It's not really that will. So what we observed experimentally is that we start reducing the surface as soon as the Fermi level in the electrode cross the redox potential of water. So how we understand that is really that you start reducing water at that point, And instead of having a constant production of hydrogen, like we will have with platinum, for instance, the radicals at the surface will just hydrogenate the surface of the diamond, passivate it, and in the end, nothing happens anymore. And so this is why diamond is such a bad catalyst for hydrogen evolution reaction, because you just completely passivate the surface and then nothing happens anymore. So the exact mechanism, I have no idea. But we were really able to measure that this was triggered at the exact redox potential of water.
Thank you.
Welcome.
Do we have time for one more?
Yeah.
So I'm sure you're going to get into some of the XAS data in the second half. Is that correct?
Yes,
so
correct.
I'll hold off on my XAS questions. Instead, I'm always curious about that positive zeta potential with the hydrogen terminated nanodiamonds. Now, in order for us to have a negative zeta potential, it seems quite logical that we have deprotonation and we have carboxylates or alkoxides that have a negative charge chemically. Now, for hydrogen termination, does this mean that we actually have an additional proton, which is giving it an overall plus charge, or do we have an accumulation of holes that's giving it the inherent positive charge? So it's non-chemical, it's actually charge related. And so if you could clarify the origin of the positive zeta potential, that would be very helpful.
The second option, at least my understanding is the second option. I actually have, I don't know if I can, because I do have a few extra slides just for that. So let me try to find them here. So you see it?
It is
All
here.
right. So basically, you can understand everything by what I was saying. So in the case of the oxidized terminated diamond, you will have a positive electron affinity. So the band will be quite low compared to the vacuum level. And if you put the numbers together, you will find out that the Fermi level in the diamond is likely to be lower than the chemical window of water between pH 0 and pH 14. That will lead to a charge transfer from the liquid environment to the diamond. And the usual way and chemical way we see that is by the deprotonation of acid group at the surface of the nanodiamond, leading to a negatively charged diamond. And that will explain the negative zeta potential and the evolution with the pH. When it comes to the H-terminated nanodiamond, in that case, the negative electron affinity, will tend to bring everything up. So the Fermi level will be above the chemical window between the pH 0 and pH 14. And this will tend to pull out charges of the nanodiamond and creating a positive charge nanodiamond. But as you rightfully say, it's very hard to understand that from the chemistry at the surface of the diamond. So my understanding is that you do have positively charged nanodiamonds themselves. And you would observe that in any kind of semiconductors, actually, with minority charge carriers just giving electrons. And because nanodiamonds are so defective, I believe that there is plenty of charge that you can get out of the nanodiamond.
Yeah, what's interesting about the current graphic on the right-hand side is that for a boron doped diamond, which is a p-type semiconductor, and the Fermi level is extremely low. In the case of any of our detonation diamond or HPHT, those are all nitrogen doped, and therefore it's an n-type semiconductor. So we're really going to have to bring that Fermi level up, you know.
Yes.
So it's interesting if we could have the same mechanism even regardless of the Fermi level, you know. And I don't think there's any boron doped nanocrystals out there.
No.
All of them are nitrogen doped.
No. And so you're right to say that in the classical picture, if we have nitrogen doped nanodiamonds, the Fermi level should be very much closer to the conduction band.
Yeah, it's going up.
Yet there are also so many defects in the nanodiamond that for me it's very hard to know exactly what is the kind of charge carriers in it. And if you look at the literature and at the measurement of the Fermi level on nanodiamonds, you can find about everything. So you have huge fluctuation of the position of the Fermi level depending on the kind of nanodiamond, the way the Fermi level was measured, etc., etc. So I mean, I would say you're right, but I'm not sure we can be that strict about the position of the Fermi level according to the nitrogen defects, if that makes sense.
Can I make a short comment? Here's Petra Fromme from Arizona State University. I joined the webinar specifically because I wanted to hear about the experiments at the synchrotrons, but unfortunately we have less than 15 minutes left. So will you be...
I go back.
When I see how many slides you have, and I have another appointment in 15 minutes, so I would really like to hear about these experiments.
So you know what? In that case, I will even jump directly there.
Okay.
Sorry, that was my fault. You can blame me.
Well, it's also me. I just talk way too much.
I also want to hear about the synchrotron experiments specifically.
So let me jump those. Okay. So I will talk about the stabilization of NV centers and some synchrotron measurements with that. So very briefly, the idea of doing synchrotron measurements is that by looking at the X-ray, we can be very interface sensitive because the X-ray, especially in the soft range, will attenuate very fast in the material, so within a few micrometers. But on top of that, what we are often probing is the emission of electrons from those photoexcitation. And those electrons will be emitted from only a few nanometers. So this is why X-ray are so interesting. We can probe only a few nanometers. And on top of that, because we are exciting core electrons of various different atoms, by tuning the excitation wavelengths of the X-ray, we can actually probe only a given element. So we can choose if we are probing the carbon atoms, the nitrogen atom, the oxygen atoms, etc. So we have element-specific information on a very narrow depths, and also we will have information on the bonding environment of those atoms. So back to the example I wanted to give you, we can talk about the NV centers. So that's a collaboration I have ongoing with Alon Hoffman from the Technion University, and Alon is designing nitrogen terminated diamonds for NV centers. So as you probably all know, NV centers can be used for probing, for instance, probing magnetic materials. And if we want to probe system, we need the NV centers to be very close to the system we are probing, and so very close to the surface. And one of the issue is that NV centers can be used only if they are negatively charged. And in order to keep the NV centers negatively charged, we need to work on the electron affinity of the surface to avoid some charge trapping. And also we need a terminal atoms that are spin friendly so that we do not interfere with the quantum properties of the center. And some atoms, so the most common one are the hydrogen. The problem with the hydrogen terminated diamond is that we will get a negative electron affinity of the surface that will tend to pull out like we won't have any electrons at the surface, so the NV will tend to be positive. Oxygen has a strong positive electron affinity, but it makes a lot of defects at the surface. And so Alon was thinking about using nitrogen for it. And so he developed many different techniques of plasma treatment for the nitrogen surface. And the way we probe it is by using both XPS and NexAFS. So XPS is X-ray. Oh, I lost it. Never mind. So basically with XPS, we excite with X-ray and we get the kinetical energy of the electrons that are extracted, and that will give you information. And the next steps, this time we look at the X-ray absorption spectroscopy. So we will look at how much each energy of X-ray are absorbed. So what we can do at the synchrotron, in contrary to the lab measurement, is that we can change the excitation energy of the X-ray. And that is particularly interesting because by doing so, we can probe different depths. Because if you change the excitation of the X-ray and you consider a given binding energy, for instance, the carbon is around 285 eV, you will change the kinetic energy of exit of the electron. And this kinetic energy will depend on, and the escape depths of the electrons will depend on this kinetic energy. So the more energy they have, the more deeper they escape from. And so we can really get very interesting information from that. So for instance, here you have spectra that we obtained on a reference oxygen diamond and on the nitrogen diamond that were treated by Alan. And what you can see is the typical spectra for a diamond with a largest peak at 285 corresponding to the sp3 bonding environment of the diamond. A peak at lower energy that corresponds to defects and surface reconstruction with sp2 carbon. And then the peak at higher binding energy corresponds to oxygen and nitrogen bonded to the carbon surface. And if you vary the excitation energy, so from 335 eV to 700 eV, you will basically probe deeper and deeper and deeper. So in the case of this nitrogen terminated diamond at 335 eV, you can see a lot of signal coming from the surface states that are at the surface and a rather limited signal corresponding to the sp3 diamond bonding. But as much as you increase the excitation energy, you will lose more and more the surface states and you will see more and more the diamond below it. And what is nice with that is that you can actually fit this evolution. So if you consider the inelastic mean free path of the electron escaping from the surface, depending on the kinetical energy of the electron, and you make a small model out of it, you can actually adjust this model on the measurements you have. So for instance, here you can see that we measured more and more sp3 component as much as we increased the excitation energy and less of the surface. And we did that with many different hypotheses on what the surface looks like. And the only convincing adjustment was actually a surface that would look like this. So we had the diamond, and then at the surface, we had some nitrogen termination of the diamond surface. And the sp2 that we observed on that surface, we figured out it's actually not surface reconstruction that the same way we can have with oxidized diamond, but we were actually able to discriminate it and find out that it is sp2 surface coverage. So basically, the plasma treatment of the diamond will create some carbon waste that would create those kind of sp2 sheets at the surface of the diamond. Another thing that we can do is that we can look at different way to terminate the diamond. So in that case, Alan also did some radiofrequency plasma. And the radiofrequency plasma was much more damaging than the microwave plasma that I presented before. And you can see here that the amount of sp2 at the surface of the diamond is huge. And so what he did is that he decided to etch this sp2 surface here, and you can see that after oxidation in liquid, this sp2 component was much reduced. And once again, we can fit those data and really extract the thickness of the sp2 layer that was formed and how much it was reduced by the chemical oxidation.
Can I ask you a brief question? Have you done this on a big crystal? So that means on a single diamond crystal or on a suspension of multiple diamonds?
So those one were done on polycrystalline diamond. So Alan was mostly working with polycrystalline and single crystal diamond. We do have a paper on nano diamond with nitrogen termination. I can send you the reference if you want. And there is also more to come. So we did like some more measurements on that. But basically they behave very similarly.
Okay, thank you.
So I talked about the XPS. What we can do is also NEXAF, so absorption. And NEXAFs will give different kind of information. So in the case of NEXAFs, we will excite electrons from the C1s core level of the diamond towards the conduction band of the diamond, but also towards surface states. So if you look at the absorption of diamond material, in the X-ray, you generally find this kind of spectra with a very strong absorption starting at around 289 eV, and this corresponds to the excitation in the conduction band. You also find out a second deep at 302 eV about, which corresponds to the second band gap of the diamond, where the density of unoccupied state is actually lower. And in case of very nice crystalline diamond, you have this sharp peak here that corresponds to the exciton of the diamond at 289.3. And I realize I actually don't have my pointer on. Yes. So here you have the exciton, this peak here. And everything below that actually corresponds to excitation of surface states. And that is very nice because by doing X-ray absorption at the synchrotron, we are able to find out where in the band gap are those surface states. So if I take, for instance, the H single crystal reference here, you can see a small feature here at 285 eV and a much larger one at 287.6 eV. And those two are unoccupied surface state. The first one are the SP2 surface reconstruction here, and the big one is the unoccupied surface stage quite high in the band gap. By doing so, we can also position the oxidized surface groups, so the double bond and single bond oxygen, and we did exactly the same with the nitrogen. So you can see that the nitrogen are slightly shifted up in the band gap compared to the oxygen. And that is very interesting when we look at the NV defects, because the NV defects lie here in the band gap. And if you have a lot of sp2 defects, or if you have some oxygen bonding at the surface of the diamond, those actually lie below the states, the NV states. And so you can have charge trapping happening. And that can lead to the blinking that we were discussing in the introduction. And in the case of nitrogen termination, this problem is way less important because the CN state are slightly more up in the band gap, so the trapping is less important. And also in case of a very well nitrogenated surface, like in the case of the microwave, you don't really have surface sp2 reconstruction because the sp2 is not at the surface, it's slightly above the surface. And so in this paper from last year or 2 years ago, we actually showed that nitrogen terminated diamond behaves better for the NV center. And if you want a bit more of X-ray spectroscopy, I will talk briefly about photoelectron reduction of CO2. So this time it's a study that we carried out in collaboration with Anke Krüger, because Anke Krüger was looking for a way to emit more solvated electrons. And the idea was to graft on top of nanodiamonds some dye, some ruthenium dye material that has a very large absorption in the visible light, in the hope that we will have some charge transfer and increased emission of solvated electrons from visible light. And indeed, if we perform some photocurrent spectroscopy, we find out that compared to classical boron-doped diamond crystal, we do have some emission of charges around 3.5 eV in the visible range. And so we try to understand this emission, and we actually also show that this emission corresponds to solvated electrons. And to understand this emission, the idea was really to measure and to plot the kind of energy scheme that I described before. So first thing first, we measure the X-ray absorption spectroscopy of the system. And you can see here the absorption spectrum. So as I presented you before, you have a very large absorption corresponding to the conduction band of the diamond. And below it, you have many surface groups. So you have the COH here, the CH group here, the COO here. And you can also see those two states absorbing a lot, which actually correspond to the unoccupied orbitals of the dye, so of the ruthenium dye at the surface of the diamond. For the occupied state, we cannot perform X-ray absorption spectroscopy. What we do is UPS, so photoemission spectroscopy. And here, once again, we find out the emission coming from the valence band of the diamond. And on top of it, you have those three features here that corresponds to the occupied state of the dye. And we can also measure the Fermi level that is just below the 3 MLCT state, which is a metal ligand state in the dye, which is unoccupied. So when everything is dry, the Fermi level lies below here. And the problem is that if you make all those measurements ex situ, we have a nice understanding of the system and how the energy levels lies compared to each other, but we cannot explain the photoemission at all. So what we had to do is we had to go into liquid. And when you go into liquid, first you need to do the measurement in the synchrotron in liquid, which is not a simple task because X-ray are actually absorbed by the liquid. So basically what we had to do is to deposit the nanodiamond on a very thin silicon nitride window of only 100 nanometers and put that into an electrochemical cell, and everything is actually under vacuum. So the X-ray go through the window, are absorbed by the nanodiamonds, and what we are detecting is the residual ionic current, which is created by this photoexcitation. And when we do that, we find out X-ray absorption graph, which is very different from the previous one. So we can still see the absorption of the conduction band and the position of the exciton. And we actually find out that everything is slightly shifted downward. And that's because when put into the liquid, you will have some oxidation of the nanodiamond. You can see also a lot of unoccupied states here. We find again the oxidation of the diamond with these features here corresponding to the CO group. And we can also see some unoccupied state within the valence band of the diamond. And that is quite interesting because it was already observed a few years before by Petit and al. And this is a demonstration that we do have a charge transfer actually between the nanodiamond and the environment. So that the publication of Petit in 2015, who observed it first. And if we look at the equilibration between the water environment, we can actually deduce that the Fermi level in liquid is rose very much, and rose so much that actually the 3 MLCT state of the ligand are populated. So just because we equilibrate with the liquid, we charge the ligand, and this state that was previously unoccupied can then be photoexcited. So another proof of this photoexcitation was also given by transient absorption that was observed in liquid and can only be explained if this 3 MLCT state is populated. And if this 3 MLCT state is populated, then we can have the photoexcitation of the diamond. And so this is how through the X-ray absorption spectroscopy and some other techniques like transient absorption, we were able to understand that it's the equilibrium of charges in the liquid environment that provides charges to the ligand and enable the excitation, the visible range, and the emission of solvated electrons. So, as a brief conclusion and outline, I want to point out that it's okay if you don't go to the synchrotron. You can still study and understand a lot about diamond surface in a lab. You can, for instance, do lab X-ray photoelectron spectroscopy, which will give you already a lot of information. And of course, you can do infrared spectroscopy in order to really understand what are the surface state of your diamond material. On top of that, to really position and understand the bond structure of your diamond material, you can do photoemission spectroscopy and surface photovoltage. So that's two techniques that you can have in your lab, and you can check this paper from 2023 if you want to know a bit more about it. And finally, if you are doing chemistry, I would suggest that you can implement very easily photocurrent cyclic voltammetry, as I explained earlier in the paper, and also electrochemical impedance spectroscopy if you want to really understand what happened at the interface. So I will also give you and let you some reference here, which are the main ones that I discussed in this talk. And I have now a bit of time for questions, if you want.
Arsène, thank you so much for this extremely interesting lecture, very in-depth lecture in very different topics. Please raise your hand or just unmute yourself and ask your questions.
Hello, I'm Alexey Legochev from Purdue University. Thanks for the talk. And my questions are about robbing NV- centers by some kind of gunk on the surface and how to avoid that. So it's the first time I hear about nitrogen termination, but have you ever compared that to termination by fluorine?
So that's something I actually wanted to do for a long time because fluorine, like according to the scheme, I did some in-depth characterization of fluorinated diamond, and one of the main interests is that the fluorine group do not have orbitals within the bandgap. So the unoccupied orbitals of the CF bond are higher. So that would virtually kill any charge transfer between the NV centers and the CF bonds. So I suspect for that purpose, it would be really, really good. But I know some colleagues who did study a bit of CF diamond for NV centers, and I think there are other problems, so I'm really not competent on that, but I think the spin situation might not be ideal. And also the compatibility of the CF surface with the environment can also be a problem.
Well, CF surface is difficult to obtain
Also,
in the first
yes,
place.
Yeah.
Compared to that, how difficult is it to create nitrogen termination?
Easier. So if you check the literature of Alan, he did great work to obtain nitrogen surfaces with plasma, microwave, radio frequency, and also ion implantation with N2 plus beam. In the case of CF, it's a bit harder. There is the chemical way by fluoric acid. That works to some extent, but you will never, in my opinion, and for what I've seen, you will never obtain a fully fluorinated surface. So far, the only fully fluorinated surface I have encountered was done with fluorine gas in high temperature environments, which is pretty nasty.
Yeah, and takes a long time.
Yeah.
Okay, thank you.
There are works on fluorine plasma. So it's one of the ways to do it more quickly from gas phase activated by plasma.
Okay, maybe.
Okay, I never heard of that, but that could be interesting, yeah.
Please, we are open for more questions.
If I may ask one, Mo Zhexie from Arizona State University, assistant professor before I was at the University of Chicago. So I'm curious to hear your opinion on how to further improve spatial resolution. So we know a lot of diamond material surfaces, especially nanodiamonds, the chemical environment are very heterogeneous, presumably. All of these kind of synchrotron or X-ray IR characterizations are rather looking at ensembles. Are there any ideas of how to sort of really look at those heterogeneities?
Yes. Well, reaching the nanoscale is very hard, I won't lie. And with X-ray, I don't know any techniques, but one thing that you could use in synchrotron and has been developed since a few years now is all what is about scanning transmission X-ray microscopy. So basically you would have a very focused, so you have two different techniques. You have one which is scanning. So you will have a very focused X-ray beam and you will just make images. And with that, you can reach a resolution of hundreds of nanometers, I would say. It will be a bit hard to go lower, but that's already something. And then you have a technique which is called tachography. No, not tachography. I forgot the name. I can look for the name if you want, but basically the idea is that you will work with the in the Fourier transform space to reconstitute the images of your probed sample, and with that you can increase a bit the resolution to tenths of nanometer.
That's a BCDI or something. Yeah.
The name? Oh, I don't know the acronym. If you have a proper name in mind, I can tell you, but otherwise I would have to look at it because I forgot. But I did some of those measurements actually on diamond. You can look, especially in polycrystalline diamond, you can have some information because you have a high resolution enough to look at the grain boundaries, for instance, or at least at different grains. But when it goes to nanodiamonds, I mean, they are way too small to do any single nanodiamonds probing.
Thank you.
And SNL, please ask your question.
Yeah, hi, thank you. My question is in regards to the photocurrent data you showed for the Rubipi functionalized diamond surfaces. You showed enhancement in the photocurrent emission at sub-bandgap wavelengths. I'm wondering, in the spectral detection of solvated electrons, did you also see enhancement in solvated electron production at these sub-bandgap wavelengths?
So here we meant, so in this particular paper, no. So we did see sub-bandgap photocurrent, but we were able to associate those photocurrent to the photoreduction and photooxidation of surface groups. And the only measurable solvated electrons we had with bandgap photoexcitation. That being said, this was with boron-doped diamond. You have many groups observing generation of solvated electrons from sub-bandgap photoexcitation, and with various understanding on the processes. There is still a lot of work to do, in my opinion. It seems to be doable. We still don't really understand what is the exact path and how we can really optimize it.
So the Rubipi, so the photocurrent that you are seeing at the sub-bandgap regime with the Rubipi functionalized surface is not due to solvated is that what you're saying?
So wait, there are two different papers. So this one is with boron-doped diamond, and the photoexcitation that you see here is actually not solvated electrons, is photoreduction and photoexcitation of surface groups. But in the last example I showed you here,
yes,
this is solvated electrons. So basically what we did is that we looked at, so we made a titration, so we made a dosage of the solvated electrons to prove that if you excite only at this wavelength, you do have production of solvated electrons. Another proof that we have of that is that we have an increase of the catalytic activity of those nanodiamonds with the dye. I don't show it here, but if you look at the paper, this paper was just published in, I forgot the name of the journal, Functional Material. So you can look at it, but yeah, in that case, we do have a solvated electron produced.
Okay, thank you.
Abe, please ask your question.
Yeah, if you could go back to the characterization of the using the XAS data. Yeah, this is a great one. So
Okay.
I remember when the small methods paper came out, and it's an absolutely great paper. I'm a big fan of it. The only thing that I view as controversial in my mind is that alcohol peak at 288.5 EV. My group has basically taken alcohols off, putting them back on, put in silica shells, put in nitrogen on the surface, and that pre-edge feature at 288.5 does not readily change with alcohol-rich diamond versus non-alcohol-rich diamond. And I'm curious if you've ever done any calculations on this, because I just don't believe the 288.5 EV feature is alcohol specific. It could be something else, maybe based on an oxide, but I find that the alcohol, the sigma star CO, is above our band gap and above our diamond hole exciton. And so I'm really waiting for somebody to do some calculations on it, but do you have any comments on how that feature is changing?
Okay. How interesting. Okay, please send me the paper you wrote about that, because that's actually very interesting. Those assignations, to be frank, are just based on literature. So I never really questioned them so far. So if you have strong evidence to question it, I think it would be very interesting to look deeper into it. I don't myself do any calculation on NextDAFs. So I can give you some names of groups doing that if you're interested to collaborate with them. But yeah, please send me some more information on that. I'd be happy to look at it.
Absolutely. Yeah, that sounds great. Thank you.
Okay, do we have any more questions? It was a great scientific exchange of information.
Yeah, I'll jump in with a quick one,
questions. Actually. Please.
Yeah. Hey, so yeah, this is Marco. This was an awesome talk. I guess one question that I had relating, maybe going to like the quantum sensing aspects that you mentioned earlier on. So when you put specifically like with an oxidized surface, and you're putting that in water, and you get band bending and some charge transfer, how does that practically affect NVs within a particle? So with regards to their T1, T2 times, things like that, what would you expect under those different situations?
So that's a very good question. I have to say, I might not be the best person to answer that, especially on the quantum level point of view. The thing I can say is that if you have, for instance, hydrogen terminated diamond, and you put that in air or in liquid environment, you would have a upward bond bending. So basically, you would have a positively charged surface up to few microns, actually. So all your NV, wow. Yeah. I mean, if you work with undoped diamond, the charge depletion thickness, layer thickness it can be huge. So you would reduce a lot the activity of your NV centers just because you remove the charge. At least that's what I expect. If you have oxidized surface on the other end, you can expect either a less upward bond bending or even a downward bond bending, depending on where is your Fermi level. And in that case, you would tend to have a more consistent negative charge on your NV centers. But you will have some trapping, etc., that can give you some more problems. This is why actually Alan developed the nitrogen terminated surface in the first place. Yeah, that's about
Could you
it.
actually jump back? There was a
but
figure that you showed with that nitrogen surface, which is what made me think of the question, where you actually had the two levels adjacent to one another.
Oh yeah, that's
it's like that's kind of what triggered this in the
this one.
Yeah.
Yeah. So what I don't show here is all the bond bending discussion. And so in this paper, we really stick to the vacuum problem. So what happens without any adsorbates. But of course, if you do the measurement in environment, you will have on top of this scheme and the possible trapping, you will have the depletion layer happening. And that would definitely affect your NV centers too. One good example is that last time I was talking with a visitor in the lab who is doing NV center probing, and she told me, well, for some of the Kelvin probe tips that we use, when we put them under vacuum, they don't work anymore. And I was like, well, that might have a lot to do with what kind of adsorbate you add to the surface and the fact that you can change the charge depletion layer. So I don't think there is any work on that yet, but that would be something to investigate because it seems to be a real problem in the community.
Yeah, this is one of this is definitely some things to think about there. I really love this figure. It's really kind of propagates a lot of questions then to go from vacuum into different environments, water.
Exactly.
Yeah, that's great. Well, thank you.
But I mean, if you have more questions, feel free to contact me in any means.
No, I have to think a little bit about it.
Okay, great. It was very good productive discussion, and everybody is free to contact Arsène or Adamas. We will contact Arsène and can continue as needed the discussions. So I would like to thank our audience for being so actively participating in this event. And again, thank you very, very much to Arsène for his beautiful lecture.
Well, thank you very much for inviting me.
And everybody is welcome to join next month. We run them monthly. There will be a talk from industry about Q1 relaxation for detection of free radicals in clinical settings. Very interesting. From the Netherlands, from QT Science company. Thank you, everyone. And we have one question from Sachin about CVD setting, which is directed to myself. Sachin, are you there?
Yes, ma'am. Thank you so much, ma'am. Actually, I'm a young research scholar working on this field.
So you asked if instead of using DMSO mixed with methanol, is it possible to use other solvents for seeding? In principle, people also use nanodiamonds in water. You can use 5 nanometer nanodiamonds and seed from water. From our experience, it was not as great seeding as from DMSO and methanol, but people definitely also actively use water-based nanodiamond slurries, which sounds more environmentally benign, right? So there is a possibility. And also Jean-Charles Arnault group developed seeding using electrostatic polymers, which also help to attract nanodiamonds from water, so you can dry those electrostatic positively charged polymer on surface and then apply negatively charged diamonds in water.
Thank you so much. Thank you so much, ma'am.
Yeah, if user questions, you can contact us by email.
Sure, ma'am. Sure. Thank you.
Would it be possible to get the PDF of today's presentation? PowerPoint, sorry.
There is recording. So it will be recorded lecture.
But also, if you want to directly contact me, I can probably extract a PDF out of it and send it to you.
Oh, okay, thank you.
Yeah, then it would be great for somebody to go and think and ask you more questions. Okay, everybody have a great day.
Thank you. It's a great talk.
Remaining time of the day. Yeah.
Thank you.
Bye-bye.
Bye for now.
Bye. Take care.
Thank you so much.